SHAP can say what mattered without telling you what would change the outcome. DiCE finds feasible feature changes that flip the prediction. You'll learn how the pieces fit into a workflow that finds prediction-flipping changes, locks fixed fields, and compares closeness with variety. I'm Professor Pi, teaching AI foundations with simple Python. Counterfactual explanations answer the simple but powerful question: what would need to be different for a different decision? That matters in loans, hiring, and any automated decision where people need actionable feedback. Feature importances tell you what mattered. DiCE gives you concrete inputs that would flip the model's answer. DiCE searches nearby points that change the predicted class while letting you lock features and restrict ranges. Picture a denied loan applicant seeing two clear choices: raise income by some amount or reduce debt by another. One choice might be smaller and easier. The other might be more distinct. DiCE hands you both, and we score them so a user can pick. We will build a tiny loan table you can inspect, train a simple logistic regression, wrap it with DiCE, lock age as immutable, and score counterfactuals for proximity and diversity so a user can choose. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's start by creating a tiny table you can read row by row. This snippet builds a tiny pandas loan table with readable features and an approval label. Feature importance starts to feel abstract when the row itself is hard to inspect, so the table keeps every column visible: income, debt, age, and approved. The PD data frame call gives us a small training set where higher income and lower debt roughly align with approval, while age is present for later immutability constraints. The code also computes an approval rate, so we get a quick baseline number to compare against after modeling. The visible output shows the approval rate, giving a quick baseline before any model or counterfactual search appears. Next, we train a simple classifier and pick one denied applicant as the local case to explain. This example trains a scikit-learn logistic regression model and captures the decision we want to flip. A counterfactual explanation only makes sense relative to a specific model prediction. So X and Y split the toy table into features and label, and those arrays drive the fit. The CLF object is fitted once, then query selects one denied applicant as the local case we will explain by indexing into the feature matrix. The code prints base prediction, so you can confirm the starting point is a negative decision before DiCE searches for alternatives. Seeing that base prediction is negative is the signal to run a counterfactual search. Now we wrap that trained model for DiCE and ask it for a few alternatives that flip the class. This code wraps the scikit-learn classifier with DiCE and asks for 3 prediction-flipping rows. Feature importance can say income matters, but DiCE turns that into candidate rows whose predicted class changes and are expressed as concrete feature vectors. The DiCEML.data object describes the training data and outcome column. DiCEML.model connects CLF through the sklearn backend, and DiCEML.DiCE creates the explainer used by generate counterfactuals. The call to generate counterfactuals requests total CFs equal to 3, which asks DiCE to search for 3 distinct flipping points. Increasing total CFs will produce more alternatives, but usually costs more search time. The visible output shows how many counterfactual flips were returned, so we know the explanation set exists. But some real features cannot change, so we must constrain the search to actionable moves only. This snippet uses DiCE constraints to keep age fixed, while only income and debt can move. A prediction flip is not automatically actionable if it changes something the person cannot reasonably change. The generate counterfactuals call narrows features to vary to income and debt. Then permitted range keeps those proposed values inside a simple feasible band, so DiCE does not propose impossible incomes or negative debts. After generation, the code inspects locked CFS and compares the age column to the original query value to verify immutability instead of assuming the constraint worked. The visible output shows immutable age changes, which should be 0 when the counterfactuals respect the locked feature, confirming the constraint succeeded. Once we have feasible flips, we want to compare how large each recommended action is and how different the options are from each other. This example scores DiCE counterfactuals with simple proximity and diversity measures. Two explanations can both flip the model, but one may require a smaller action while another gives a more distinct option, and we want numbers for that trade-off. The pandas arithmetic compares locked CFS with query on income and debt, normalizes by each feature span so features are comparable, and averages the action size into prox, which is a simple proximity score. The combinations logic builds pairwise gaps between counterfactuals, and np.mean summarizes their spread as div. The visible output shows average action size beside option spread, making the proximity diversity trade-off inspectable instead of just qualitative. If you map this tiny demo to a real bank pipeline, the same steps apply. Make a readable feature table, train a stable classifier, generate constrained counterfactuals with DiCE, and then rank suggestions by how easy they are and how distinct they are. Use it when you need concrete, user-facing suggestions that actually respect what a person can change. Use it to turn opaque denials into actionable next steps. One caveat: counterfactuals inherit model bias. So if the model is unfair, the alternatives will reflect that. And you must audit inputs and outcomes. A practical next step is to increase total CFs to 10 and compare average action size and option spread across runs to tune how many alternatives you present to users. If you want smaller actions, try tightening permitted range for income and debt, and watch average action size fall. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.